Hey everybody, this is section 8.2, L'Hopital's rule. When we are taking the limit as x approaches a, whoops, wrong one. Limit as x approaches a of f of x over g of x, and really what L'Hopital's rule is about is first of all taking the limit of fractions, but these fractions have variables usually both in the numerator and the denominator. If we cannot find the limit by just simply plugging in x equals a, and if the fraction, when we do plug in a, produces 0 over 0, for example, we put a value in for f of x and you get 0, put the same value in for g of x when you also get 0, that's called an indeterminate form. We can't divide by 0, of course, and 0 divided by 0 is not 0. It's indeterminate. We don't know what the limit is. It could still exist. Theorem 4 says L'Hopital's rule, the first form. Suppose that f of a equals g of a equals 0. So you plug a in and you get 0 in for both of them. That f prime of a and g prime of a exist, so the derivatives have to exist, of course. And that the derivative of g does not equal 0. If it did, then we would still be dividing by 0. We can't do that. Then the limit as x approaches a of f of x over g of x is the same as taking the limit of the derivatives of each. So let's look at example 1. We have an indeterminate form. Estimate the limit graphically and then use L'Hopital's rule to find the limit. Well, first of all, if we plug 0 in, we get 1 plus 0 minus 1 over 0, which is the square root of 1 minus 1 over 0, which is 1 minus 1 over 0, which is actually 0 over 0. Now that's important because if we plug in the value and we don't get 0 over 0, that's not an indeterminate form like we have up here. So we do have 0 over 0, and L'Hopital's rule should give us the actual limit of this. So we have the limit as x approaches 0 of the derivative of 1, the square root of 1 plus x. We have 1 plus x, that's to the 1/2 power. So that's going to be 1/2 times 1 plus x to the negative 1/2. The derivative of negative 1, or just 1 in this case, it goes away, it's 0. And then the derivative of x is 1. So all this here is divided by 1, which we really don't have to worry about. So we have the limit as x approaches 0 of 1 over 2 times the square root of 1 plus x. Now we can actually plug 0 in and not get an indeterminate form. We have 1 over 2 times the square root of 1 plus 0, which is 1 over 2 times the square root of 1, which is simply 1/2, and that is the actual limit of this function. Sometimes after differentiating the new numerator and denominator, both equal 0 at x equals a. As we will see in example 2, in these cases we apply a stronger form of L'Hopital's rule. Now all this says is that you can keep taking derivatives as long as you get an indeterminate form. So let's look at example 2 here. We have the limit as x approaches 0 of this function. Now let's plug in 0. Let's see, we would have square root of 1 plus 0 minus 1 minus 0 over 2 over 0 squared. Now we would get square root of 1 minus 1. 0 over 2 is 0 over 0 squared. 0 squared is 0. And we would get 0 over 0. That is the indeterminate form. Let me erase this because now I'm going to run into my other work. We have the limit as x approaches 0. We have the derivative of the square root of 1 plus x, which is, again is 1 over 2 square root of 1 plus x. You can see the example before if you want to see that written out a little bit more. The derivative of 1 is 0, and the derivative of negative x over 2 is minus 1/2. And on the bottom we have 2x. Now if we plug in 0 into this function, we'd get 1/2 minus 1/2 on top over, that'd be 0 on top, and then 2 times 0 is 0, so we would still get 0 over 0. So we can do L'Hopital's rule again. We have the limit as x approaches 0 of, let's see, I think I want to rewrite this radical again as 1/2 1 plus x to the negative 1/2. That's really what the derivative of the square root of 1 plus x is. This is going to be easier to take the derivative again because we'll have negative 1/4 times 1 plus x to the negative 3/2. The derivative of minus 1/2 is 0, and on the bottom now we have just simply 2. Now let's see what we get when we plug 0 into this function. We have negative 1/4 times 1 plus 0 to the negative 3/2 over 2, and that's equal to, well, 1 plus 1 to the negative 3/2 is just going to be 1. 1 times negative 1/4 is just negative 1/4, and so we have negative 1/8, and that is the limit of that function. But the point being on example 2 is if you take the derivative, get an indeterminate form again, you can just keep taking the derivative as long as you get indeterminate forms. In example 3, we're using L'Hopital's rule with one-sided limits. It says, evaluate the following limits using L'Hopital's rule. In A, we have the limit as x approaches 0 from the right of sine of x over x squared. If you plug 0 in for sine of x, you get 0. Plug 0 in for x squared, you get 0. There's your indeterminate form. So this would produce 0 over 0. So let's take the derivative. Limit as x approaches 0 from the right. Derivative of sine of x is, of course, cosine of x over 2x. Now if I plug 0 into the top, I get cosine of 0 over 0. So we get 1 over 0, but now we're approaching this from the right. Now imagine finding values that get closer and closer and closer and closer to 0. Well, let's grab the calculator, investigate that a little bit. Close this. I know that doesn't work. So let's pick a very small number, but to the right of 0. For example, instead of plugging in 1 over 0, we plug in cosine of 0.0005 over 0.0005, and of course 2 times that. And let's see what we get on our little calculator here. So we have cosine of 0.0005, and then divide that by 2 times 0.0005. And what you're going to get is a very large number. Now, the closer you get to 0, the bigger that number is going to be. So when you get 1 over 0, it's a one-sided limit. It actually goes to infinity. Infinity is the answer for that one. Now, what about if we're approaching 0 from the left? Once again, if we plug 0 in for x, we get the indeterminate form 0 over 0. So we have the limit as x approaches 0 from the left of the cosine of x over 2x. Now, if we just plug 0 in, of course, we're going to get 1 over 0 again. Well, what if we changed the 0.0005 into negative? So I'll do an entry, get that back up, do an insert, make it negative, and go all the way over here, do an insert, and make that negative also. And we get negative 999. So this thing is actually approaching negative infinity. And there we have it.